Hey, what's up, guys? This is Sheng here. So today, let's take a look at LeetCode number 1467, probability of two boxes having the same number of distinct balls. Mm, so this one is a hard problem, and I think it's a pretty tricky math-related problem. It's about the probabilities, also the combinations and the permutation stuff. I think at least for me, every time when I try to see like a probability problems, and if it's a hard level, it's always I have to scratch my head quite a while to figure it out, or not. So okay, so let's take a look at the description. So you're given like two n balls, right? Of and k colors, and so the way the ball is giving you is like you're giving like a ball's array here, right? So and the index I means that it's the color I, and then the value for the index I means that how many balls for that color. Okay, and then all the balls will be shuffled uniformly at random. Basically, this is like a sign of the all the possible like combinations or permutations, right? Basically, your goal is to distribute these two n balls into two groups, right? So one group has n balls, the other one also has n balls, and so note that the two boxes are considered differently. So for example, if we have two balls of color A and B, right? So AB is different as BA. So basically AB and BA we count as two different scenarios. Okay, and we want to calculate the probabilities that the two boxes have the same number of distinct balls. So, I mean, the same number of distinct balls. Basically, what does it mean? It means that the two boxes should have the same number of colors. That's what that's what the last sentence is telling us. So if the box, uh, so first, right? So first, each of the box should have the same number of n balls, and among those kind of n balls, right? We have n balls in box one, we have another n box in box B. So it doesn't really matter how are those kind of balls consist of, as long as this one has the same number of colors, distinct colors as this one. So for example, if this one has three colors, this one is also needs to have three colors, right? And we want to calculate the probabilities of that, right? So and let's take some examples here. And so if we have like two balls, right? Basically for color 0, right? So if we use index for color 0, we have one ball, and for color 1, we also have one ball. So how many ways we have, like the total different ways we can distribute this balls, right? So we have two ways, okay? So which means that we could put ball 0, this the color 1 into box 1, and then the other one into box 2, and then vice versa. That's why uh, that's why this 0 1 and 1 0 we treat it as differently, right? So these are like two scenarios. I mean, so here 0 is a color, right? And then 1, so the first scenario we put color 0 in uh, color 0 into box 1, right? So this is a box 1, this is a box 2. That's why the total scenario for the first one is 2, and the total valid, right, scenario is also 2. That's why the probability for the first one is 1. Okay, and then here's like a more complicated case. So here we have, okay, so he's using like a one base color. So now we have for color 1 we have two balls. That's why we have 1 and 1, right? And then for color 2 we have one ball. That's why we have a color 2 here. And for color 3 we also have 1 here. And the output is like this one, basically the 2/3. So how do we get that? So as it describes here, so the total distinct shuffles, or the total distinct distribution is 12, and out of the 12 we have 8 valid shuffles. Okay, right? So that's the all the 12 totals, total like shuffles, the scenarios, and out of those things, which one are not valid. So this one is not valid, right? This one is not because the box one only has one color, right? The box two has two colors. So and this one is not valid either, right? Similarly for this one and this one, right? So those are the four invalid scenarios, and all the rest 8 ones are the valid one. That's why we have 8 divided by 12, which is this number. Cool. And yeah, so here are some more examples here. Now here we have 6 balls in totals, and the total possible scenarios or shuffles is like 180. And then for this one we have a 0.6, and then so on and so forth. Okay. The constraint is like seems like pretty small. Like we only have like 8 balls. Sorry, 8 colors, and in each colors we have up to 6 balls. This one seems pretty small, but if you do like a factorial things, that the total combinations with this kind of in total of 48 balls, right, will be too huge, too big basically. So that will definitely TLE. If you try to use the brute force way to solve it, right? Okay, so to solve this problem, so it seems like we already have like some of the idea here, right? So basically, uh, the total the final answers, it just should be the valid count, right? So be the valid count, right? Valid. Okay, sorry. Valid count divided by the total counts, right? So that's gonna be our goal here. And let's see how can we calculate that. So first, since we're given like some examples here, let's try to see how does this total number come from, right? So for example, let's say we have 211. So it says the total will be 12, right? I mean, if it's a pure permutations, so what's gonna be the total total like scenarios for this, since we have 4 balls, right? So it's going to be a 4 factorials, right? So it's going to be a 4 times 3 times 2 times 1, which is like 24, right? But for this one, it's 12. So why 12? It is because we have like 2 balls has the same color, right? Which means that, as you guys can see here, so for this one, for this kind of scenario, the scenario here, if we switch these two ones, it doesn't. We're still counting this one. It's not like a new scenario, right? But if we switch this 2 and 3, then it's a new shuffle, right? But for these two numbers, they are the same. That's why so for this one we have to do a 2. Actually, it's a 2 times 2 factorial. That's why we have 12. Okay, and how about another example here, right? So we have 6 balls, right? So the total permutation for this one without considering the duplicated colors here, it's going to be 6 times 5 times 4 times 3 times 2 times 1, right? 6 factorial here. But so this one, what's this number? This is like the 720, right? So that's the total numbers. But it turns out we only have like 180 possible scenarios. So how do we get that? Basically, this is like, since we have like two same colors here, so it's going to be a 2 factorials, and then we have another 2, right? So that's why we multiply these two together here, right? So it's going to be a 720 divided by 4, which is 180, right? So now we have like we have find the formula to get at least the total scenarios. Basically, it's going to be the total number of balls of the factorial of the total number of balls divided by the by by any by the factorial count for any of the balls who has the same color, right? That's going to be the way we calculate the total. Okay, just keep this in mind. So we'll use this formula later on to help us get the valid count. Okay, cool. So now the question is, how can we efficiently calculate the valid count, right? I mean, we can somehow distribute it, the balls one by one, right, into different groups, into two different groups. But if we do that, right? But if we do that, I mean, we also need to consider the basically the duplicate scenarios, right? So actually, it turns out to be let's say we have some balls here, right? We have some. Okay, so it turns out, actually, what we can do here is that all we need to do is that we just need to basically, our goal is to split this kind of balls into two groups, right? And if let's say we already have some groups, we have this one groups, right? This one, and then we have another groups here. Okay, so these are the two boxes, right? With this kind of thing. So assuming that these two groups are valid groups, right? Which means that the basically the total number of the balls are the same, and also the color, right? The distinct colors are the same as well. So if that's the case, right? Let's say we have what? We have the let's say we have two zeros, right? And then we have two ones, and then we have one two. We have one color with one ball with color two. So let's see. This is the the count of each color in this box one here. Okay. So what does this one mean? It means that actually the order of this box doesn't really matter, because as long as we can make sure they have this kind of exactly number of the balls here, we can freely shuffle it, right? So basically for this one, we can rearrange the colors, the balls, right, in different scenarios, and it turns out the 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 total different combinations within this B1 is exactly the same formula as this one. So what does it mean? It means that we have five balls and we have 2 to 1, right? So the total different scenarios for B1 to get to B1 is what? It's the same thing. It's basically it's a 5 factorial divided by 2 factorial and then times 2 factorials. So basically that's the total combinations, like, or different shuffles within this B1, given this kind of like number of the balls. So similarly for B2 here, right? So for B2 we also have like similar like formula here, depending on how many balls, right, and what colors there. We can use a similar of that, and then in the end we just need to do a multiply among those two like scenarios between the B1 and B2, and that will be the total, basically the total number of the scenarios, or you can call it the cases, given this split scenario, and we need to accumulate uh, this kind of counts, right, for all the split scenarios. Basically, we need to enumerate all the possible ways to split these two n bars into two groups, and within each of the stat scenario, we have to validate, check if that split is a valid split. If it is, then we're gonna calculate the total counts on the left side and the total counts on the right side, and then we're gonna multiply that value together. That will be the total number count. Yeah, I think that's pretty much the idea of that. You know, even though this you can, I think there's also like some other solutions for this problem, but I think for me personally, I find this one is the easiest one to understand. And okay, I'll try to explain a little bit more why I'm trying to implement that. Okay, so first, since we are going to calculate a lot of factorial values here, right? And we need to pre-calculate those factorial values. And since the total number of the balls is limited to what times 6 times 8, which is 48, we can just pre-calculate the factorial numbers until 48. Okay, so I'm going to factorial number as like list, right? So I'm going to put a 1 at the beginning, I in range of the 1 to 49, right? And then the factorial dot append factorial, right? The -1 times I. Okay. So the reason I put 1 here is because, so when we try to use the factorial, let's say, this factorial array is a 0 based. But when we try to get the factorial, let's say we're trying to get the factorial of 5, right? So 5 is 1 base, right? That's why, if we do 5 here, it means that we're looking for the 6th element in this factorial array. That's why I prefix it with 1. So that, when I calculate the factorial 1 here, when I do a times 1 here, it will not affect that result. Okay, so that's a little trick here when we calculate the factorial here. And then let's say what we have. This one's the colors, right? So the length of the balls is the number of colors here. Okay. And then we have this kind of backtracking method, right? Since we're going to try to distribute those balls into those different two groups here, right? So I'm going to use the backtracking method here. And then in the end, right? So we just need to return the. So let's say we have total, right? So total equals to some number here, and then we have the valid count equals the backtracking. So I'll use the backtracking to calculate that, right, with some parameters. And then in the end, I just need to return the valid count, right, and then divide by the total, right. So and to calculate the total, the total, I'm going to define like helper functions, So remember, so we have this kind of 6 factorials divided by 2 factorials times 2 factorials, something like that. So in math, this thing is called multinomial. Okay. So for this one, I'm going to pass in a box, right? So it's gonna basically this box is a list of integer. Okay. So it means that how many how many balls for each color in this box, right? And then so we have the total, which is the sum of box, right? So the total means that how many balls in total in this box, right? And the way it works that since we're going to do some calculation for this one, right? So at the beginning, the answer will be the factorial of the total, right? And then we just need to find do like a division by the count for each of the color, right? So basically for count in the box, right? So now the count means that how many balls for this color, right? We just do an answer divided by this factorial of the count. And then in the end, we return the answer. So that's the helper functions to help us to calculate this kind of result, right? And okay, so once we have that, and then for the total, actually it's going to be a multinomial here of what of boss, right? So I mean, for the total, we can think it as the as a big box, right? Who has everything? That's going to be the total. So now it's the valid count. So to calculate the valid count, I'm just simply using a backtracking method here. So we have an index, and then we have box 1 and box 2. Okay, so and basically, if the index is equal to n, right, it means that we have already distributed all the balls, right? So the reason being, I didn't use the total number of balls instead I'm using a color series that because later on here, when I do this thing, I'll basically for each of the color, right, we have count 1 in the range of balls of index. Okay, I'll explain what I'm doing here. So I have a for loop here in the end here. It means that with index, right? So the balls index is giving us the count for the current colors, right? So what this for loop is doing, that I'm trying all the possible distributions for this count of the current color, which means that we have count 2 will be the balls. So count 1 is the count that I'll put into the into box 1. So which means that the count 2 will be the balls that will be put into the box 2 here. So that at each of the backtrackings, I make sure I have already distributed all the balls for the current color. That's why I can just simply stop when we have consumed all the colors. Okay, cool. So now we have count 1 and count 2 here, right? So and we can just do first we check if the count 1 is not empty, right? And then we do a box 1 dot append to count 1, right? Because again, right, so the box 1, we only cares about how many how many balls for the current colors. We don't even care about what color. All we care is this count, right? And again, that's why we do a +1, right? Because the count itself, let's say it's 5, right? We want to make sure we try all the distributions from 0 to 5, right? So that's that. Similarly for the count 2, right? So we have count 2. It's going to be the box 2 dot append count 2, right? And then accumulate this thing with backtracking method, right? And then we have this index +1, right? That's going to be the color index, and then we have a new box 1 and a new box 2, right? Because we want to accumulate all the valid scenarios for all the possible split distributions for the current colors, and then we accumulate that thing together with current answers. And then, of course, we have to do the backtrack, right? So count 1, then box 1 dot pop, and then same thing for the count 2 here. We have box 2 dot pop, and then in the end, I simply return the answer. Yep. So basically, that's the way I try all the possible distributions for the for each color, right? Now it's the exit point here. So whenever we have consume all the balls, right, or you can say all the colors. So first thing we want to check is that if the length of the box 1 is equal to the length of the box 2, right? So this one means that if the length of the box means that how many colors in this box, right? So remember, so what do we save in this box 1? We only store the for the same colors, we only store the count for this color, right? So which means that the length of the box is the number of the distinct colors in the current box. So that's how we check that. And then we also want to check if the sum of the box 1 equals to the sum of the box 2, right? So this one, it's guaranteeing that it's a valid each box will have like each box will have like the same number of balls. And since we have consumed process distributed all the balls, this one means that the two groups have that have the same number of boss. And if that's the case, right, we can just return the combination, which is going to be the multiple nomial, right? This time we pass in the box 1, right? Since we're going to calculate those scenarios separately. Similarly, same thing for the box 2. Okay, and in the end we just multiply them together, right? Else what? Else we simply return 0, right? Yep. So I think that's pretty much it is. So if I run the code here, oh sorry. So when I call this one, so pass in 0, empty, and empty list. Okay, run the code, accept it, and run it. Yep. So there you go, right? I mean that's basically how it works. And so for this kind of backtrackings, maybe we can do a little bit improvements uh, by cutting some unnecessary branch here. I mean, what we can do here is that uh, so we can do a sum1 equals to this sum box here, and then sum2 equals to this sum box 2 here, and whenever if the sum1 is greater than than half of the total of balls, right? Or the sum2 is greater than that, there's no need to continue because we know there's no way we can get the second condition, right? So to get the total ones, we have n here. Actually, let me reorganize this code a little bit so that I can put everything below here. Okay, so we have factorial here, and so we need a total boss. Basically, total boss gonna be the sum of the boss, right? So I can just use this one to check if this one greater than the half of that, right? Or sum2 is greater than the total boss divided by 2, right? So if that's the case, we can simply return 0, right? Because there's no need to continue. That's going to be early termination for our backtracking method. And let's see if we submit this one more time. Let's see. Yeah, so as you can see it's a little bit faster than the previous one because we cut some unnecessary branches, right, for this backtracking. Yeah, I guess that's pretty much it is for this problem. It's a pretty tricky like math problem plus backtracking, and yeah, and I think the most important thing for this problem is that you have to be able to figure out. I mean, the how can you calculate the total combinations, right? Given like some like balls, right, consist of different colors. And then the next one is that you have to be able to basically realize that as long as we can fix like a split, right, like a split of the distribution into two groups, and all we can simply just calculate the total permutations for each of the group, right? And then we can just multiply those two counts together to get the final result, so that we don't have to try. So that basically we don't have to try all the permutations inside each of the group here. We can simply use the count for the colors to quickly get the total permutations for that specific box or group. Yeah, I think that's it. Yeah, I think I'll just stop here, and thank you for watching this video, guys. Stay tuned. See you guys soon. Bye bye.